Hello, Mr. Dashel. How are you?
I'm fine, sir. Thank you.
Is everything okay?
Yes, sir.
Good. So, Dashel, good to see you again. So, this is our third lesson about modular arithmetic. It's all about remainder, usually it's related to integers, right? When you just divide an integer by another integer, okay, if it divides without any remainder, it's fine. But usually, how about if it leaves remainder and how things are related to each other? Anyway, today we will talk about inverse. Actually, this inverse, it is a mathematical term that is used in different topics, and depending on the context it has some different meanings, but after all the general meaning is the same, like inverse function, a multiplicative inverse of a number, inverse of a fraction, and blah blah blah. But here we will use this idea to solve some modular equation, let's say equation that involves modular arithmetic. Anyway, so in the previous section, we understand that the signs that's congruent and equal, they have some similar properties in addition and subtraction and multiplication, right? If you remember, for example, let's say A is congruent to B modular M. Just some example. If you remember, if A is congruent to B mod, let's say it is M, right? So that means that if you just add something to both sides, again, we will have the same thing. Like, for example, A plus C is congruent to B plus C mod M. And also, if you just multiply by the same number, here we have A times C, it still is congruent to B times C modular M. And also, if you just subtract, we will say the same thing, okay? But again, in here, actually, we did not define or use any division operation, right? If we don't have that, for what happens if I just divide both sides by, let's say C and C, because we don't have division operation in modular arithmetic. But here we are just going to introduce this in some different way, okay? Because, and also in real number system, how do you define division? Division is just the inverse of multiplication, right? So it's actually, in this sense, we are going to introduce this division operation. Let's just start with this definition. If there is an integer, C, so we are given some kind of integer C, such that C times A is congruent to 1 mod M or modulo M. So that means that if you just divide the C times A by M, right, the remainder is 1. Then the C is called the inverse of A modulo M, and denote this as A inverse. Okay, so here, for example, that means that if you're given here, we have a kind of integer, right? The product of two integers. When you divide this by M, the remainder is 1. Example, if we have, for example, 6, right? 6 is equal to 2 times 3. So that is congruent to 1 modulo, for example, 5. So see here, 2 times 3 is congruent to 1 modulo 5, which means that here 2 is the inverse of 3 modulo M, or 3 is the inverse of 2 modulo 5. Okay, this is how we, introduce the multiplicative inverse. So let's just say the division operation here. So here, what is 2? So I can just write here, 2 is the inverse of 3 modulo 5. So that I can just write here 2 is equal to 3 minus. Actually, here this minus is not the power, okay? It's not like 1 over 3. Maybe you can understand 1 over 3, but actually it is the inverse of 2, which satisfies this condition. So that C times A is congruent to 1 modulo M. So that means that C is the inverse of A. Okay, so now this theorem says that if M is, what is this, a positive integer. The positive integer means it is 1, 2, 3, 4, 5. And also the highest common factor of A and M is equal to 1. So this parenthesis A and M, how did you define this? we define is as the greatest common divisor or the highest common factor. So the highest common factor or the greatest common divisor of A and M is equal to 1. So here we have two conditions. M must be positive integer and the highest or greatest common divisor of A and M must be 1. So if these two conditions are satisfied, then A has an inverse modulo M. Okay. So why actually here we have this condition, okay, and one, we can see that actually if, for example, I'm just counter example, suppose that A and M is not equal to 1. Let's say some number K, where K is not equal to 1. At the time, it doesn't have inverse. Why? Because A has an inverse modulo M, right? So that means that A has inverse means, so here we have A, so inverse, let's say it is B, okay, B is congruent to 1 modulo M, right? And so here M is greater than 1 and the modulo M. And so inverse means here we have such integer B so that A times B, when you divide by M, the remainder should be 1. Again, by definition, how we understand this congruence, that means that A times B minus 1 is equal to, right, that is divisible by M. So that means that here we have M times some number. Let's say it is P. Okay. Now from here, it just take -1 to the right hand side, MP to the left hand side. So here we have A times B minus M times P, A times B. On the right hand side, we have 1, right? And since this A and M, they have a common factor of K, right? So that means that this A, I can just write it as K times some number. Let's say this A1, B. And also this M, I can just write it as K times some number. Let's say it is M1. And here we have P. On the right-hand side, we have 1. Let's see here, we have K. That's why this condition is a mass condition. If we just take K out, here we have A1, B minus M1, P. On the right-hand side, we have 1. And what is K? It is an integer that's not equal to 1. Actually, it's a positive integer. And do we have what actually any integer where not actually, which is not equal to 1 times another integer, the product is 1. We don't have such integer, right? Only the product of two integers is equal to 1 if and only if it is -1 times -1 or 1 times 1. Otherwise, actually, we don't have any other integer. We cannot show any different integer which is not equal to 1. That product of two integers is equal to 1. And that's why this is a mass condition. If the highest common factor of A and M is not equal to 1, that means that A doesn't have an inverse modulo M. So now just immediately we just have a look if M is greater or equal to 1. Okay, we don't have problem here. So if the highest common factor of A and M is equal to 1, then we can say that A has inverse. The next question is, the problem is, how do you find the inverse of A modulo M? Now I will try to answer this question. Okay. So let me just delete my writings. All right. So it is trivial that if A has an inverse, then there are many other numbers which are inverses of A. Because when you just say inverse, we talk about the classes. Okay, it's a class actually that contains those a lot of infinite many numbers actually. So it has this property that what is it? The property is A times that its inverse is congruent to 1 modulo M. So example, for example, 2, 3, 2, 7, 12, and dot, dot, dot is -3 and -8, maybe -13 and -80, blah, blah, blah. These are all inverses of 3 modulo 5. Because if you multiply, for example, here, 3 times 2 is congruent to 1 modulo 5. And how about 7? 3 times 7, 3 times 7, that's 21 divided by 4. Again, it's 1 modulo 5. Or 3 times -3 is also, it is 1 modulo 5. It is 3 times -3 is -9, right? -9, we can just write it as 2 times, actually minus 5 times -2 plus 1. Okay, so in the following discussion, the inverse of a certain number refers to the corresponding congruence class. So I want to just say actually the inverse, actually we just talked about the class. So we can just usually find only one of them as a representative elements. That will be enough to actually, how to say, to solve our problems. So if they ask us to find more, we can just write them a few elements and following that pattern. It just gives us the understanding that that class contains those numbers like 2, 7, 12, minus 3, 8, dot, dot. We understand that to get some other elements, just we need to keep adding 5 or adding -5 here. Okay, so when we solve congruence equation that AX is equal to B, right, mod M, we multiply both sides of the equation by A inverse. Actually, that is the general rule in solving these equations, right? So like even if you just solve, for example, here 3 times X is equal to, let's say it is 9. But how do we actually find 3? But in real number system, we can define division. That division is actually defined as the inverse of this 3. Okay, what is this X? So I should multiply to get this, to leave this X alone. I need to multiply both sides by the multiplicative inverse of 3. So what is multiplicative inverse of 3? That means that when I multiply 3 by another number, it should be equal to 1. What is that number? That is 1 over 3. So here we multiply both sides by 1 over 3 times 3 times X equals 1 over 3 times 9. Actually, what is this 1 over 3? It is multiplicative inverse of 3, right? That's just defined as 3 to the power of -1, or 3 in the index, it is -1. So, but actually, what is it? In modular arithmetic, we did not define division. That's why I'm just going to label this inverse by a to the power of -1 here. So now again, we are just solving this simple equation, right? Simple equation. Okay, in real number system, we know how to solve this. The procedure is very similar. So now to leave X alone here, right, we should just multiply both sides by the inverse of this A. So now I'm multiplying both sides by A inverse and also A inverse, because we know that by the theorem, right, if you just multiply both sides by the same number, it does not change anything here. So next, we just multiply this. What is A inverse times A? That's just equal to 1, because A inverse A, that's equal to 1 mod M. So that means that now on the left-hand side, only X is left. How about on the right-hand side? On the right-hand side, we have A inverse times B mod M. So actually, usually we use this theorem to find the, what is it? The remainder of dividing a big numbers by some integer. I will see them in the example soon. So that is X is equal to A inverse times B. Okay, so now the question is to find this X. Okay, so we have two methods to find an inverse of a number in modular arithmetic. The first one is extended Euclidean algorithm. Now we are going to say this in two examples. The second one is the Euler theorem. Of course, this Euler theorem is kind of the general methods because this extended Euclidean algorithm is a kind of very basic method. If the number is small, we can use this extended Euclidean algorithm. If the number is big, using this extended Euclidean algorithm, it will be quite long. So at the time, we'll just use the Euler's theorem. Now let's just start with the first one, extended Euclidean algorithm. Okay, does 23 have inverses or inverse modulo 37? Okay, there's a lot of inverses, but here we should find only one. So if it has, find one of its inverses, right? So to answer this question, first we have to check that what is the greatest common divisor of 23 and 37? Is it equal to 1 or not? If it is equal to 1, the answer is yes. Yes, 23 has inverses modulo 37, right? Otherwise, it doesn't have. Since we know that the highest common factor of 23 and 37 is 1, because the only common factor they share is 1. They don't have any other common factor except for 1, which means that actually we call this in math, what is it? They are relatively prime numbers, or co-prime to each other. Relative prime means the only common factor of these numbers is 1. Such numbers are defined as relatively prime numbers. Anyway, since 23 and 37, right, the highest common factor of these two numbers is 1. So then 23 has inverses modulo 37. That is, okay, the answer to the first part of the question. The second part is, what is this? How do you find this? So if x is the inverse of 23 modulo 37, because I don't know that thing, right? You're just going to find that x. So what does it mean? It means that since x is the inverse of 23, that means that if we have 23 times x should be congruent to 1 modulo 37. We need to have this equation, right? So now using this one, then 23x is congruent to 1 modulo 37. And by definition, what we understand this from here, it's just a kind of different notation, right? That means that actually, if you remember, a is congruent to b modulo n, which means that a minus b is divisible by n, or n divides the difference of these two numbers. So by the definition, that means that 37, right, divides 23x minus 1. And divides means that if you divide 23x minus 1 by 37, the quotient will be some integer. So that integer is y. Suppose it's y, I can just write it as 23x minus 1 is equal to 37 times y. So this y and x, these are some integers. Or I can just bring this into a simple, our usual algebraic equation, because take -1 to the left-hand side and 37 to the left-hand side. What do we have here? 23x minus 37y is equal to 1. Okay, so now the idea here is, of course, the question here is we need to find some integer. When I substitute for x and for y, it must satisfy this equation, right? The 23 times x minus 37 times y should be equal to 1. Okay, how do you find this? By the extended Euclidean algorithm, we can find such combination of x and y. Maybe sometimes trial and the guess, or guess and trial method also it may work. Okay, so if it doesn't work, now in the table I'm going to show this, but before I move to the next slide, let me just show you how we are finding those x and y. So let me just start from 37 here. Okay, so actually this Euclidean algorithm is this. So first, I try to express everything in terms of 23 and 37. How? So 37 is equal to, if you divide it by 23, the quotient is 1, the remainder will be is 14. Right. So now I see here in this relationship, I have 37 and 23, but I don't have 14. I can express this 14 in terms of 37 and 23. Now I will just move this to the left-hand side, and I will move actually this 14 into the place of 23. So now here we have 23. If you divide it by 14, again, the quotient is 1. The remainder is, what is it? It is 9. So I have 23 and 14 is good, and 14 can be expressed as a linear combination of 37 and 23. And how about 9? Again, I just move this 14, put 14 here, and here we have 9, and the quotient is 1. The remainder is 5. Again, if we just continue this process, so 9 moves to the left-hand side. Here we have 9 is equal to 5 times 1 plus 4. Right? So now the last one, let's see here, just move this. So here we have 5 is equal to 4 times 1 plus 1. So I just continue this until we have a remainder of 1. So now I will just actually move this in reverse order. Okay, starting from 1 here. Let me just change the color here. So 1 is equal to, take 4 to the left-hand side, 5 minus 4 is equal to, from the previous one, okay, I have 5 here, right? I can express 4 in terms of 5. So 5 minus, what is 4 in this equation? 4 is 9 minus 5. So here we have 9 minus 5. That's equal to 5 minus And let me just simplify this. Minus minus is plus. So here we have plus. Which I can just write it as 2 times 5 minus 9 equals. Now from the previous one, now instead of 5, I can write 14 minus 9. So here we have 2 times, what is 5? It is 14 minus 9. So here still I have 9 here. Let me simplify again. 2 times 14 is 2 times 14, and 2 times negative 9 minus 9, that is minus 3 times 9. Okay, so now, okay, now we have 14. That's a good thing. But now I need to change this 9 in terms of 23 and 14. So what is 9 here? 9 is 23 minus 14. So equals 2 times 14 minus 3 times, instead of 9, I can just write here 23 minus 14. So again, if you simplify this, minus minus, it is plus 14. How many? We have 5 14s. Minus 3 23. So now I have 14, right? The last one, I can change or express 14 in terms of 37 and 23. So that's equal to, what is 14? Here we have 5. 14 is 37 minus 23. And minus, here we have 3 times 23, which is equal to, if you remove the brackets here, 5 times 37 minus 5 minus 3 minus 8 times 23. Okay, so as see here, the last result, here we have 5 and here we have 8, right? So this 8 times 23, as see here, 8 minus 8 times 23, and the 5 times 37, that's equal to 1. I can just actually write it here. So here we have 23 times, what is in front of 23? It is minus 8. Minus 37, here we have 37 times minus 5. On the right hand side, we have 1. So actually, what is 8? We were looking for this x, right? Now from here then, what is the inverse of 23 modulo 37? So here we can just write here, minus 8 is the inverse of 23, or let me just write here, minus 8 is an inverse of 23 modulo 37. So actually this method is called extended Euclidean algorithm, how to find the inverse of the function. Also by table, actually this, we can just guess and trial what happens if x equals 1, y equals 0, or x equals -1, it is 1, or it is 2, -1. Or in this, we can just continue to see here, when x equals -8, y is equal to 5, the remainder is 1. And it's just, what is it? Tabulated form of what we have just done in the previous slide. So -8 mod 37 is the inverse of 23, or -8 is the inverse of 23 modulo 37. Dasha, is everything clear?
Yes, sir.
Good. I mean, if everything here clear, no need to show any other example. Or if you want, I can show you one more example, like what did, for example, let's say like 17x is congruent to 1. For example, let's say this modulo, what is it? Let's say this 43, right? As see here, this 17x, we're just solving this modular equation, or equation involving modular arithmetic. So this 17 times x equals 1, and the first observation is solution. The first observation here is, as you see, the highest or the greatest common divisor of 17 and 43 is equal to 1, which means that we have such x, right? It exists. It has the inverse, because not every number has inverse. So it has inverse. Now we need to find this. So how can I change this into the equation again? So that means that the 17x minus 1 divides 43. That means that that's equal to 43y. Or if you just take 43y to the left hand side and 1 to the right hand side, and 17x minus 43y is equal to 1. Now, of course, the number, if the numbers is small, directly you can just guess and try. If it works, you can just pick it as an answer. But numbers are a bit big. For example, here, I don't know, you can just guess what numbers are this. It may be a little bit hard. So that's why I'll just use that Euclidean, extended Euclidean method, okay, the algorithm to find this x and y. So let me just start with 43. Okay, it doesn't matter you start with 17 or 43, but 43 is a bigger number. That's why I want to start with 43. So now if you start with 43, 43 is equal to 17 times 2. It's 34, it is plus 9, right? So that's equal to plus 9. 34 plus 9 is, it is 43. So now next thing is I move 17 to the left and also 9 into the place of 17. So here we have 17 is equal to 9 times 1 plus 8. And here again, here we have 9. 9 is equal to 8 times 1 plus 1. Now we already got 1, right? So when just we have the remainder as a 1, we should stop this. Now, if you just move in the reverse order from here, what is 1? 1 is equal to 9 minus 8. 9 minus 8. So what is 8? 8 is 17 minus 9. So 9 minus, what is 8? 17 minus 9. Or immediately, let me simplify this. Here we have minus minus plus. So it is 9 times 2 minus 17. Now from the previous one, what is 9 now? 9 is 43 minus 17 times 2. So that's equal to, what is 9? Let me just write 2 first here. It is 43 minus 17 times 2. So still I have 17 here. So equals 43 times 2 and minus 417, one more 17. So that is minus 17 times 5. So our equation is 17x minus 43y equals 1, right? So I can just write it as 17 times minus 5 and minus 43 times minus 2. On the right hand side, we have 1. So which means that actually this is our x. So that x is equal to negative 5. What does it mean? It means that negative 5 is so dot 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 negative 5 is the inverse of what? The inverse of 17 modulo 43. Okay. And of course, if you just add, for example, 43, it will be, what is it? 38, or 38 is the inverse of 17. If we have to find the smallest positive, let's say, number at the time, what is it? It will be 38, right? 38 is the inverse of 17 modulo 43. That means that if you multiply 38 by 17 and subtract 1 and divide by 43, you will get an integer. Okay, that's actually what is the extended Euclidean algorithm. This is how we find the inverse of a number which is given in this equation. Okay, of course the condition, our condition is, what is it? The highest common factor of this a and this m, it should be equal to 1. All right, so now let's continue. Before we move to the second methods, okay, first we have to introduce something new. We call this Euler function. Okay, this phi, this is how we read this. That's a Greek letter. It's denoted by this Greek letter phi, phi of n, or just phi n. So phi n represents the number of positive integers, that is m less than or equal to m, where m is relatively prime to n, or that is co-prime with n. So what is this? That means that like simply, what is phi n? Phi n is a number, some kind of number here, okay, where, so this one is less than or equal to m, that's less than or equal to n, and the highest common factor of this m and n should be equal to 1. And this is how we define this phi of n. It's a function. How should we read this? It is a number. This phi of n is a number, right? What is it? It is the number of, actually the numbers between, in this set. Here we have, let me just write here. Here we have 1 and 2 and 3 dot dot, and here we have n. Okay, and here the number of elements in S, which is relatively prime to the number m. Okay, this is how we denote this. For example, let me just write here phi of 8, for example. Okay, so phi of 8, all right, the number of positive integers, okay, so which are relatively prime to 8. If you just write, for example, some of these numbers, 8, 1, the highest common factor 8, 1 is 1, and 8, 2, it is 2, and 8, 3, it is 1, and 8, 4, it is 4, and 8, 5, it is 5, and 8, 6, it is 2, and 8, 7, it is 7, and 8, 8, it is 8. This 8, 7, it should be 1. Okay, so that means that which of these numbers are relative prime to each other. Here, let's see here, this is 1, and this is 1, and also this one is 1. So we have 3, right? So here that means that, so the value of our function here is this phi of 8 is equal to 3. So that means that 3 numbers from this set, right, from 1 to 8, actually they are relatively prime to 8. What are those numbers? They are 1 and 3 and 7. Right. And actually, if this 8 is, this n is equal to prime number, simply I can just write that thing here. Okay, maybe. Okay. So how about if n is a prime number? If n is a prime number, then this phi of n is always equal to n minus 1, right? Because all the numbers except for n, they are relatively prime to this number. For example, let's say phi of 5, for example, that's equal to 4. Why? All the numbers like 1 and 2 and 3 and 4, they are relatively prime to 5 because 5 is a prime number. If it is not prime, then the only way is to find this one. Of course, we have different methods, so we will take it, give it as a theorem. So find the value of phi of 10. That means that how many numbers between 1 and 10 inclusive are relatively prime to 10. It means this. This is how we should understand this function. So phi of 10 represents the number of positive integers that is less than or equal to 10, where m is a relatively prime or co-prime to 10. So what are these numbers? Again, if you just write this 10, 1, the highest common factor of 10 and 1, it is 1. Highest common factor of 10 and 2, that is 2. Highest common factor of 10 and 3, it is 1. 10 and 4, it is 2. 10 and 5, it is 5. 10 and 6, it is 2. 10 and 7, it is 1. And 10 and 8, it is 2. 10 and 9 is 1. 10 and 10, it is 10. So now if you just highlight where the highest common factor is 1, is 1, 2, and here we have 3, and here we have 4. So now we can just write here then the value of this function. So that is phi of 10 is equal to 4. Okay. Now you see here, okay, when the number is small, we can use this method. But when the number is too big, like let's say this 500 or 1,000, even 10,000, right? That method is not a practical way to find the number of cofactors or the number of numbers which is relatively prime to n. So now we have a kind of the result of that theorem. Like a corollary means it's a result taken from a main theorem. So here it says that first, let's express n in prime factorization. You know that every positive integer or every integer, even it can be expressed as a form of prime factorization, right? We can just find the prime factorization of any number, right? For example, let's say it is 10. 10 is equal to 2 times 5. The powers are 1. And 2 and 5, they are prime numbers. Like 24, for example, I can write it as 2 cubed times 8, it is 3, right? Or 35, or let's say 70, for example. 70, we can write it as 2 times 5 times 7. Or 100, right? You can just write it as 2 squared times 5 squared. These are the prime factorizations of these numbers. This is how we find them. Of course, if you just have a big number, you can just make a column and start dividing by the smallest prime factor, like 2, and after that divide by 3 and 4 and blah, blah, blah. In this way, we can find the prime factorization of any integer. Okay, now suppose that we are given n, and this p1 to the power of a1 times p2 to the power of a2 times dot 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 pr to the power of ar. That is the prime factorization of the number n. Then our Euler function, this phi of n, is equal to this. Now here we are not going to prove this. Okay, we can just take this as a fact and use this to solve our questions. So this phi of n is equal to n times 1 minus 1 over p1, 1 minus 1 over p2, 1 minus 1 over p3, dot, 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 1 over 1 minus 1 over 1, 1 minus 1 over pr. Okay, this is a very good way, okay, short way of finding this phi of n. Example, apply the corollary to find the value of phi of 10. Right, to find this phi of 10, again, solution. So here this 10, we can just write it as 2 times 5. Now from here, this, what is phi of 10 then? This phi of 10 is equal to 10 times 1 minus the first prime factor, that is 1 over 2, times the second one is 1 minus 1 over 5. Which is equal to 10 times 1 minus 1 over 2, 1 over 2, 1 minus 1 over 5, that is 4 over 5. If you simplify this, as actually agrees with our previous finding, right, that's equal to 4. Or another example, how about, since we're talking about the 70, right, what is phi of 70? Right? And what is 70? 70 is equal to 2 times 5 times 7. So that's equal to 70 times 1 minus 1 over 2 times 1 minus 1 over 5 times 1 minus 1 over 7, which is equal to 70 times 1 minus 1 over 2, 1 over 2, 1 minus 1 over 5, 4 over 5, 1 minus 1 over 7 is 6 over 7. So the 70 over 2 times 5 times 7, that's equal to 1. So that's equal to 24. So that means that we have 24 numbers between 1 and 70, which are co-prime with 70. Dashan, is everything okay?
Yes, sir.
Okay. All right. And how about if you are given a big number, 1408, right? How do you find the Euler function? I mean, the value of this Euler function. So one way is, of course, we need to find its prime factorization, 1408. I draw a line here. That is one fastest way of finding all prime factors of or any big number. Divide by 2. Here we have 7 0, 4. Now still we can divide by 2. It is 3, 10, it is 5, and here we have 2. Divide by 2, it is 3, 1, 15, it is 7, 12, it is 6. Divide by 2, it is 8 and 8. Divide by 2, 44. Divide by 2, 22. Divide by 2 is 11, and divide by 11, that is 1. So here we have 1, 2, 3, 4, 5, 6, 7. So 1408, we can write it as 2 to the power of 7 times 11. Now to find the phi of 1408, that's equal to 1408 times 1 minus 1 over 2, 1 minus 1 over 11, which is equal to, it's too bright, 1408 times 1 minus 1 over 2, 1 over 2, 1 minus 1 over 11, that is 10 over 11, which is equal to, if you divide this by, what is it, by 2, it is 704, and divide by 11, so that's equal to, what is it, 7, 6 left, okay, 2 to the power of 6, so that's 64. So 64 times 10, that's equal to 640. Okay. Now let's talk about our main theorem then. Okay. So this theorem 8 says that is the Euler's theorem. If the highest common factor of a and n is equal to 1, then a to the power of this phi of n is congruent to 1 modulo n. That is the most important theorem of this lesson, let's say. So we are going to use this theorem to solve the problems. So this is the Euler theorem. So it says that if the greatest common divisor of a and n is equal to 1, then a to the power of this phi of n is congruent to 1 mod n. And we know how to find this phi of n, right? So if a of n is equal to 1, according to Euler theorem, now we have a to the power of phi of n is congruent to 1 mod n. So by using this index, right, we know that, for example, a to the power of m, I can just write it as a to the power of a to the power of m minus 1. And using this, also this a to the power of phi n, I can just write it as a times a to the power of phi of n minus 1, because here we have 1, right? So that is actually, here we have a times a to the power of phi n minus 1 is congruent to 1 modulo n. And since this a, right, a to the power of phi n minus 1, what is it? Both numbers actually, modulo n, what is it? So they are co-prime, right? It is co-prime. So that means that this a to the power of phi n minus 1 is congruent to 1 mod n. No, I need to write something here. Small mistake. This a to the power of phi n minus 1 mod n is the inverse of a. So that means that if you multiply a and by this, it is congruent to 1 mod n, which means that this number is the inverse of A mod n. Inverse of A means that your product is equal, is congruent to 1 mod n. That means that your product, if you divide by n, still they leave a remainder of 1. Anyway, now let's see this in the example. For example, in modulo 10, find the inverse of 7, right? So solution, let's just use this Euler's theorem in this example. In modulo 10, find the inverse of 7. So that means that here we have 7 times x is congruent to 1 modulo 10, right? And here the question is, what is x, right? So first, since here we have 7, the highest common factor of 7 and 10 is equal to 1. So this x exists. So now from here, I'm going to find this phi of 10. What is phi of 10? We have already found this. That's equal to 4, right? Because that's equal to, what is it? 10 times 1 minus 1 over 2. Let me just write here. That is 10 times 1 minus 1 over 2 times 1 minus 1 over 5. That's equal to 4. So which means that then what is x then? This x is equal to, right? Here we have 7 to the power of phi of 10. This one is phi of 10 minus 1, which is equal to 7 to the power. What is phi of 10? Is 4. So 4 minus 1, that's equal to 7 cubed. So which means that now here dot, 7 cubed is the inverse of 7 modulo 10. So that means that if you multiply 7 and 7 cube, right, and divide by 10, the remainder will be 1. So which means that here we have 7 cubed. What is 7 cubed? 7 cubed is, it is 343. That is congruent to 3 mod 10. Okay. All right. So now we are going to solve a few examples. Time is it? 18. We have 17 minutes. All right, good. For the following set of numbers a and b, find the greatest common divisor of a and b. If a b is equal to 1, then find the inverse of a modulo b by the extended Euclidean algorithm. So let's start with the first one here. And what is 9 and 15? Both numbers are divisible by 3, so that's equal to 3. So that means that it doesn't have inverse, right? This 9 modulo 15, right? It doesn't have inverse. How about 4, 9? Here, there's 4 and 9. The highest common factor is equal to 1. So that means it exists. So now we need to find this then. This 4x is congruent to 1 modulo 9. So which means that again here we have 4x, right? Minus 1 equals 9. Why? So that is 4x minus 9y is equal to 1. But I guess in trial, I think we can get this. What is x here? So x is equal to 2 and y is equal to negative 1. Here we have y equals negative 1, x equals negative 2, right? So this negative 8 plus 9 is equal to 1. So now here dot, negative 2 is the inverse of negative 2 is the inverse of 4 modulo 9. Okay. Another example, maybe you don't have to solve all of these questions, okay, because they are similar. Let me just do one of them here. How about D? And since here 24 and 17, right? So that's equal to 1. So 24 has the inverse modulo 17. So now we need to solve this equation that 24x is congruent to 1 modulo 17, because here A equals 24, B is equal to 17. So by the equation, what do we get here? Here we get 24x minus 17y is equal to 1, right? Okay, 72. How do we get this? Starting with 24. 24 is equal to 17 times 1 plus 7, right? So now 17 is equal to 7 times 2 plus 3. And 7 is equal to 3 times 2 plus 1. Now we have 1, so just stop here. So now from here, what is 1? 1 is equal to 7 minus 3 times 2. So 7 minus 3 times 2 equals 7 minus 2 times, what is 3? 3 is 17 minus 7 times 2. 17 minus 7 times 2. Or if you simplify this, here we have 7 minus 2 times 17, that is 17 times 2, and minus plus 4 times 7. So there's 5 times 7. So here we have 5 times 7 minus 17. Now 7, I can express it in terms of 24 minus 17, right? So 5, what is 7? 7 is 24 minus 17. And here we have 17, which is equal to 24 times 5 minus 5 minus 1 minus 17 times 6. So now if you just write here, and I can just write as 24 times 5 minus 17 times 6. That's equal to 1. So dot, dot, dot. And what is this x? So here x is equal to, here we have 24 times x, right? That is 5. So which means that 5 is the inverse of 24 modulo 17. Okay. These are similar examples. Let me just skip them. Question 2, find the values of the following Euler function. And also you know how to find them. Let me just do only one of them. The big one is 5040. Let's just do F. So to do F here, 5040, right? So first we have to find its prime factorization. Okay, divide by 2. Here we have 2520. Divide by 2, it is 1260. Divide by 2, it is 630. Divide by 2, it is 315. Now it's not divisible by 2. Divide by 3, 105. Divide by 3, it is 35. Divide by 5, it is 5. And by, it should be 7. 7, 1. So these are 2s and 2 3s and 1 5 and 7, right? So now then, let me just write here phi of 5040 is equal to 5040, 1 minus 1 over 2 times 1 minus 1 over 3 times, it's a bit, okay, small, I need more space. So phi of 5040. 5040, 1 minus 1 over 2, 1 minus 1 over 3, 1 minus 1 over 5, 1 minus 1 over 7. Or that's equal to 5040 times 1 over 2 times 2 over 3 times 4 over 5 times 6 over 7. So this 2, 2, it is gone. And also this 3, 6, it is gone. Here we have 2, here we have 8. So, okay. And we have to divide it by 35. And if you divide it by 35 and multiply by 8, right? So 5040 multiplied by first 8 and divide by 35. So that's equal to 1152. Let's check the time. Okay, we have 9 minutes. Good. That's it. And actually we have three questions, and they have a lot of sub questions. I'm just trying to solve maybe 1 or 2 from each. We are running out of time. Anyway, question 3, for the following set of numbers, A and B, find A and B. I mean the highest common factor of A and B, and find the value of phi of B. And if the highest common factor of A and B is equal to 1, find the inverse of A modulo B by the Euler theorem. Okay, so let's start with the first one. 2, 3, right? So 2, 3 is equal to 1. That's our first step. Okay. Number 2, phi of B. What is phi of 3? That's just prime number, right? So that's y is equal to 2. And if the highest common factor of A and B is equal to 1, find the inverse of A modulo B by the Euler theorem. So by the Euler theorem, right? So we know that here it is equal to 2. So A, what is A? It is 2. 2 to the power of actually 2, right? This 2 is congruent to 1 modulo 3, right? So then what is the inverse of 2? The inverse of 2 is dot, dot, dot. The inverse is A inverse is equal to 2. Okay, that means that the inverse of 2 is equal to 2, because this 4 is equal to 2 times 2, right? So the inverse of 2 is 2. And how would the second one be? And here we have 3 and 5, the highest common factor is equal to 1. And number 2, phi of 5, 5 is a prime number, that's why is equal to 4. And number 3 is, since it is 4, right, 2 to the power of phi of 5, which is equal to 4, is congruent to 1 mod 5, right? Because 2 to the power of 4 is 16. If you divide by 5, the remainder is 1. So actually this 2 to the power of 4, I can write it as 2 times 2 cubed, that is congruent to 1 mod 5, which means that 2 cubed is the inverse of 2 mod 5. Okay, we have a lot of examples. Let me just do one question and I will finish it, okay? And here, for example, the 78 and 13, right? And 78, the first step, and 13, it is equal to 6. And that's why it doesn't have inverse. I mean, 78 doesn't have inverse mod 6. And how about 117, number 1, and the highest common factor of 117, that is congruent. This is just last example, that is 1. And number 2, so we need to find phi n, right? So 100, we can write it as 2 squared times 5 squared. So that is phi of 100 is equal to 100 times 1 minus 1 over 2 and 1 minus 1 over 5, which is equal to 100 times 1 over 2 times 4 over 5. That is 10. 10 times 4, it is 40. So number 3, now we need to find that since it is so, that means that here we have 100, right? So 100 to the power of 40 is congruent to 1 mod 17. So that means that if you divide this number 100 to the power of 40, right? If you divide by 17, it is 1. And since this 100 to the power of 40, I can just write it as 100 times 100 to the power of 40, 39 is congruent to 1 mod 17, right? So from here, dot, 100 to the power of 39 is the inverse of 100 mod 17. Also, other examples are similar. Using the same method, we can solve this. Dasha, thank you very much for this week. Okay, that's it. Next week, we also have questions from the test. That means a kind of revision test. And we will finish this course. Okay, Dasha, do you have any questions for me?
No, sir.
Okay, then take good care of yourself. Okay, enjoy your weekend. I will see you next Sunday. Okay, bye-bye.
Goodbye and thank you, sir.
Thank you.